Hello guys, welcome to another episode of Random Solvings. So today we're going to be solving the integral that measures the universe. So I saw this somewhere on Instagram, and then I thought it was interesting to share with you guys because this is also an important integral, especially those of you in engineering and analytical mathematics. Okay, straightforward. The answer is pi over 2. But someone will say, how comes? How is this integral pi over 2? So I'm going to show you how we get a pi over 2. And for this particular integral, I will introduce you to a technique in integration that you might not know before, but it's called the Feynman. Okay, so Feynman's technique, it's what we're going to be using. And along the line, you might see me making reference to some Laplace transforms or using standard reduction formulas for integration. But don't be scared. I already assume that at this point, you already know some standard integral and you know a little about Laplace transforms. If you don't know about Laplace transforms, in my channel, I prepared a lecture on Laplace transform. You could just watch in one of my videos on engineering mathematics, and you'd see where I give the basics of Laplace transforms and some important Laplace transforms you should know for some important functions. All right, so let's dive into it. So how do we use the Feynman's technique? The Feynman's technique here is kind of like related to the Fundamental Theorem of Calculus. For instance, let me just give you a hint. Whenever you have integral from b to a of some f prime of x dx, you know that this is eventually an f of a minus f of b. Okay, this is kind of like the fundamental theory of calculus. Of course, if f is continuous in the interval between a and b. All right, so we're going to try to rewrite our integral. So this is not Feynman's technique, okay? I'm just trying to remind you of some fundamental theory of calculus, FTC. So these are the fundamental theory of calculus, okay? And Feynman's technique borrows some knowledge from the fundamental theory of calculus. So in this approach, you're just going to try to rewrite your integral. Let me call j my integral. My integral is j, the integral from 0 to infinity of sine x by x dx. Okay, I've called this j. So I'm going to use the Feynman's technique by defining a new function I of s is integral from 0 to infinity. And what we usually like doing is to introduce this dummy term, exponential minus sx, all right, to the integral sine x by x dx. So the reason why I'm introducing this dummy term is, as you can see, I'll call this equation 1. If I take I of 0, of course, you would have 0 infinity exponential 0, of course, because s times 0 is 0, of course, sine x over x dx. And this is just integral from 0 to infinity sine x by x dx. And this is our original integral j. Is that okay? If I take I of infinity, all right, and then we plug in infinity into this integral. Let me just do it the casual way. So you have exponential minus, I'm not supposed to write it like this, but let me just do it, minus infinity x sine x by x dx. I'm going to have roughly, because this term is going to go to 0, okay, when you have exponential minus infinity, it actually goes to 0. So 0 times anything is 0, so the whole integral results in 0. So you can actually see that if we subtract both sides, all right, if I subtract both sides, I of 0 minus I of infinity is equal to j minus 0, which is equal to j. Okay, do you guys understand that? So in other words, my j, which is my integral from 0 to infinity, right, which is sine x by x dx, is still the same thing as solving I of 0 minus I of infinity. Is that okay? So we're going to keep this as, let me call this equation, I already labeled equation 1, so I'll just call this equation star. Is that okay? So this is okay, I of s, so this is 1 and this is 2. Is that okay? So I hope you're flowing with me up to this point. So the most important thing is you being able to define this particular term in the integral and see if you could do some manipulations, and just make sure that I of 0 is your main integral and make sure that I of infinity is 0. Is that okay? So if you can do this, you're going to get an expression in equation star that our integral is evaluated as I of 0 minus I of infinity, and of course I of infinity is 0. But the most important thing is we using our knowledge of this definition over here, this definition in equation 1, we're going to use this definition to do wonders. Okay, we're going to use this definition to find an expression for I of s. Okay, so that we can evaluate I of 0 minus I of infinity. So the goal is to find I of s. So when you're using Feynman's technique, the goal is to find I of s. Okay, all right, as a function of s. Is that okay? So if you can do that, you're good to go. So we can remember that we defined our I of s as this integral from 0 to infinity exponential minus sx, where s is just a dummy variable, and you have sine x by x dx. Is that okay? So the next thing we usually do is to find the derivative. I prime of s is actually d by ds of I of s. So we're going to differentiate this whole integral with respect to s. Okay, so you're differentiating an integral with respect to s. So if you differentiate this with respect to x, this is what you're going to get. So because we assume that the function inside is continuous, so we could just change the order of terms. So this is 0 to infinity d by ds of exponential minus sx sine x over x dx. Is that okay? So this gives me, when I differentiate this term with respect to s, I'm going to get integral from 0 to infinity. I'll get minus x exponential minus sx. Of course, remember when you differentiate exponential minus ax with respect to x, you're going to get a exponential ax. If you differentiate with respect to a exponential ax, you're going to get x exponential ax. Is that okay? I hope you remember these rules of differentiation. So we are differentiating with respect to s, so we're going to get minus x exponential minus sx. Then you have sine x over x dx, and at this point x can cancel out, so that we now have minus integral from 0 to infinity exponential minus sx sine x dx. Is that okay? So this is my I prime of s. Is that okay? So since I have my I prime of s like this, we'll now try to solve this integral so that I can get an expression for I prime of s in terms of s. And when I solve this integral on the right hand side, I will now integrate it, okay, to get I of s. So without much talks, what we're going to do is we're going to evaluate this. Now I'm going to use two ways to evaluate this. Okay, first I'm going to go through the long method of evaluating this, and then I'll show you a much more shorter way of evaluating this. Okay, and most of you will be surprised. Now let's evaluate this using the long method. So we should recall some standard reduction formulas. Okay, now when you have integral of exponential ax sine bx dx. Check your reduction formulas. This gives me exponential ax all over a squared plus b squared into, you have a sine bx minus b cos bx. All right, so this is what you get when you integrate this. Okay, so I'll leave this to you guys to figure it out. All right, figure it out by yourself. So, or look up reduction formulas, or if you want me to do a video on how this formula was derived, you could just leave a comment in the comment section. Is that okay? All right, so I'm going to use this standard integral to evaluate this particular integral, and I'll have my I prime of s is the minus integral from 0 to infinity exponential minus sx sine x dx. So in this case, my a is minus s and my b is 1. Okay, if you compare this, my a is minus s and my b is 1. So I'm just going to use this formula and I'll get minus. So I'll put a square bracket, okay, and then I'll put exponential minus sx all over my a square is minus s squared, which is s squared, plus my b is 1, and into my a, of course, is minus s sine x bits b equal to 1, okay, and minus b is 1, and you now have cos x. So this is our integral. All right, so this is going to be the answer of this integral. Then remember, it's a definite integral. We have to solve it between 0 and infinity. So solving it between 0 and infinity implies that, of course, when you have a minus sign, you can make things quite easy for yourself. This minus sign can reverse the order of your definite integral. So you have your definite integral become exponential minus x into s squared plus 1, then minus s sine x minus, you have cos x, yes, and this becomes 0 infinity. So how did I put 0 infinity here? It's just the effect of this minus sign. Whenever I have a minus sign, I could just use it to change the order of my integration variable. Is that okay? So I'm gonna go to new pane. So what we have right now is we have I prime of s is equal to e to the minus sx over s squared plus 1 minus s, yes, sine x minus cos x, all evaluated from 0 to infinity like this. So we have my I prime of s is equal to, so I'm going to plug in 0. Okay, so plugging in 0 into this whole stuff, you know that this will become 1 because exponential, you're solving this integral when x is 0 and when x is infinity. So when x is 0, you have 0 times s gives me exponential 0, which is 1. So I have 1 all over s squared plus 1. And of course, what happens to this term? Sine 0. Of course, you know sine 0 is 0. Is that okay? Sine 0 is 0. So these first terms cancel. And minus cos 0. Cos 0 is what? 1. So 0 minus 1 is a minus 1. Is that okay? So plugging in 0 into this integral gives me this term. So minus. So plugging in infinity. I won't just plug in infinity like this. I'm going to do it in a more refined mathematical way. I'm going to say limiting value as x tends to infinity, exponential minus sx all over s squared plus 1 into minus s sine x minus cos x. Is that okay? So this is how to solve a definite integral. When you have terms involving infinity, you substitute the first term normally, but when you have infinity, it's better to use a limit. So using a limit helps us to understand what happens in the limiting case. And of course, this limit is going to cause this term to go to 0. Why is it going to go to 0? Because when you plug in infinity into this exponential, this x of course, becomes infinity, and exponential minus infinity gets to 0. So whatever is the outcome of this term here, because this term is 0 over here, or this term approaches 0, then this whole limit is going to be 0. And then our I prime of s is just minus 1 all over s squared plus 1 at the end of the day. Is that okay? Because this term goes to 0. And now we have gotten our I of s in terms of s, so we can actually integrate both sides with respect to s. So when we integrate, I'm going to get I of s is going to be integral of minus 1 over s squared plus 1 ds. Is that okay? So when I integrate, this is actually a familiar integral. This is minus integral of 1 over s squared plus 1 ds. And if you remember your standard integrals, this is minus tan inverse of s, okay, plus my constant. So the derivative of tan inverse of s gives me 1 all over s squared plus 1, in case you forgot about that. So at the end of the day, our I of s is just minus tan inverse of s plus c. Is that okay? All right, so let me keep this here first of all, and actually use a shorter approach to arrive at this point. So these equations star star. Now remember that what we did previously. Was we tried to solve our I prime of s is equal to I prime of s is equal to minus integral from 0 to infinity exponential minus s x, yes, sine x dx. Is that okay? So this is what we tried to solve, and then we use standard integration formulas. But if you are actually very smart, you can actually see that this is actually related to something you already know. Maybe you just need to change these terms. This is sine x exponential minus s x dx, and this is actually the Laplace transform of sine x, if you remember. All right, so do you remember that the Laplace transform of a function f is actually integral from 0 to infinity? Let's assume our function is causal, meaning that it is defined for 0 to infinity. So we have your f times maybe exponential minus st dt. Is that okay? So this is the definition of the Laplace transform of a function. So the Laplace transform of sine x is sine x times exponential minus sx dx. Is that okay? And of course, we know the Laplace transform of sine x. We know that the Laplace transform of sine ax is, of course, a all over what? S squared plus a squared. So the Laplace transform of sine x is, you have a minus sign here. With a being 1, you have 1 over s squared plus 1. And this is just the same thing that we got previously, you understand, using our standard integral, right? That's what we got at this point. So using our standard integral, we got that the whole integration gives me minus 1 over s squared plus 1. But everything is actually encapsulated inside your knowledge of Laplace transform. Okay, if you know the Laplace transform of sine x, of course, you're just going to get the answer quickly. And at this point, you can get your I of s by just integrating with respect to s. 1 over s squared plus 1 ds, which is minus integral of 1 over s squared plus 1, yes, ds. And this gives me minus tan inverse of s plus c. So this is my I of s. So we've gotten an expression for I of s. So you need to remember, to wrap up our answer, we remember that our j is equal to the integral from 0 to infinity, yes, of sine x over x dx, and we got this as I of 0 minus I of infinity. If you can remember, in our definitions, we defined this earlier somewhere in equation, we defined it over here. Yes, we defined it in equation star. That's our j is I of 0 minus I of infinity. So now that we've gotten an expression for I of s, Now that we've gotten an expression for I of s, all we just need to do is find I of 0. So I of 0 is minus tan inverse of what? 0, okay, plus c, which is actually c, because tan inverse of 0 is 0. Is that okay? And you have 0 plus c, c. Now my I of infinity is minus tan inverse of, with s being infinity, plus c. And of course, tan inverse of infinity is 90, and 90 is actually pi over 2. Is that okay? So this is minus pi over 2 plus c, or I can write it as c minus pi over 2. That's my I of infinity. Now, since our j is the answer to my integral, j is integral from 0 to infinity sine x by x dx, which is I of 0 minus I of infinity, c minus pi over 2. And of course, when you evaluate this, you get pi over 2. And this is how this integral becomes pi over 2. Thanks to the Feynman technique, we have evaluated the integral, yes, pi over 2. So this is a very, very important function. I'll just say a few things before I round up. Sine x over x is an important function, especially sometimes they write it as sinc, okay, sinc x. Some standards agree to write it like this, and this is a cardinal sign. It looks like this. It looks like this, and so on and so forth. And each of these cottons, it's at integer multiples of pi, 2 pi, 3 pi, 4 pi, and so on and so forth. And this falls as 1 over x. Is that okay? So this is the cardinal sinc function. You could use the decimals to actually plot sine x over x, and you discover that it gives you this kind of shape, sinc cardinal sine shape. For those of you that are into signal processing and signal analysis, you're going to encounter this shape a lot. So you should start studying about it. And now we are getting to see that when you integrate the cardinal sign over half of the period, when you integrate it, you're going to get pi over 2. Is that okay? So pi over 2, meaning that when you integrate it from minus infinity to infinity, you're going to get pi. Is that okay? So you should try perhaps to see if you can figure it out. So before we round up, I'm going to leave you with an exercise. So can you actually tell me what is going to be, let's say I define k as an integral from 0 to infinity cos x by x dx. So tell me about the answer to this integral. Does it converge to something like pi over 2, or does it diverge? So use your knowledge of standard integrals. For instance, we know that if you have an integral of exponential ax sine bx dx, and I told you this is exponential ax all over a squared plus b squared into a sine bx minus b cos bx. All right, so if you have integral of exponential ax cos bx dx, you're still going to get exponential ax all over a squared plus b squared, and of course this is going to be a cos bx plus b sine bx. Okay, so this is what you're going to get. So you can use your knowledge of standard integrals, or you can use your knowledge of Laplace transform, and tell me what will be the answer to this integral. Does it converge? Does it diverges? So I'll leave it for you as a proof. So thank you for watching, and I hope you learned something today. It might have been confusing, but it just shows that you need to refresh some standard integrals and refresh your Laplace transforms, and yeah, everything will be all right. So come back to this Feynman's technique. It's a very important technique used in integration, and I hope you guys enjoyed it so far. If you have any questions at all, or if you have suggestions or problems you want me to solve, you could feel free to leave it on the comment section and I'll look at it in my free time. So once again, thank you for watching, like and subscribe, and see you next time. Bye.